right, today we're going to talk about potential energy and kinetic energy and harmonic motion, all with a block on a frictionless plane, which is attached to a spring. When the block is attached to a spring on a frictionless plane, if you move the block back and forth, back and you let it go, it oscillates. It goes back and forth, and you have an example of a harmonic motion, simple harmonic motion. Let's look at the setup. The force here is equal to the spring constant times x, however much we pull it. X is 0 is equal to 5 centimeters. V0 is equal to 0 centimeters because we're not going to let the block move until we let it go. And so V0, it's 0 at time 0. And we have the harmonic oscillator function, x, a function of t, equals c cosine of omega t plus theta. This is an arbitrary extra phase. It becomes less arbitrary when we put in the initial conditions. So if we put in the initial conditions, we'll end up with theta equal to 0. Let's do the derivative first, though. The derivative of x with respect to t is equal to minus sine times the sine of wt plus theta times dwt dt, which is equal to w. So I put the w out here, and we do it again for the acceleration. And so you'll end up with another w out here, and it'll go then from sine to cosine. It goes from cosine to sine to cosine, and there's a minus sign that follows from the velocity. If we want to put in the initial conditions, x0 is equal to 5. Theta, we don't know what that is at this point, and we don't know what c is. But if we say sine of theta is equal to something, sine of theta has to equal 0, so theta has to equal 0. So we're going to put theta as 0 in both these cases. We're going to put 0 here and 0 there, so the thing simplifies, and c then becomes 5. So we can erase c here, and we can finalize our answer for given the amount of information we have. This is our final answer for x, dx dt, and dx squared dt squared, or x, velocity, and acceleration. Well, we also want to talk about the mechanical energy here, and also we know that that's equal to the kinetic energy always plus the potential energy. But kinetic energy is 0 when we first start, so it's equal to just the potential energy. So what we want to do is now figure out what the potential energy with respect to x is for a spring, and we look at the derivative of potential energy with respect to x, and we get the derivative of kx to x, which implies that that's equal to k. And so the derivative of the potential energy integrated over the whole, period is equal to the integration of kx dx, which is equal to 1/2 k x squared, which is 25 over 2k. And that is the end of the problem. Can't put kx here because we don't know that yet. So here I just split this from here down to here and put the dx over here and the dp here, and that integrates this into what we know as the potential energy. See you later.